So now that we have some new tools in our toolbox, let's see if we can take them out and do some stuff with them. What I want to focus on now is how we can use all the information that we know about rational functions, intercepts, domains, these new asymptotes we've been talking about, how we can use all of these tools to come up with a reasonably accurate sketch of a rational expressions graph, right? And this is kind of just the general process we're going to follow. First, we're going to factor and simplify things. I want to emphasize this. The simplified version is not usually going to be exactly equivalent to the original one. We're going to have to keep track of any factors that we cancel out, right? Because if you cancel a factor out of the denominator, the original function is still undefined at that point. So we're going to have to take that into consideration when we're doing the graph. Then we're going to think some about transformations. Sometimes we can get a graph really easily that way if we can think of our new function as being a transformed version of one that we already know. Then we're going to think about intercepts. Then we're going to think about asymptotes. That may not necessarily be enough. We may still be left with a position of asking, well, is the graph above the asymptote or is it below it? All right, and to clarify that, sometimes we are going to have to pick a point, find the value of the function at that point, and use that to make that decision. All right, so let's look at some examples. All right, starting off with this guy, -1 over x plus 1. Now, when I look at this, the first thing I notice is there's no variables in the numerator, and all I have in the denominator is an x. Right, so this immediately kind of brings into my head the function f of x equals 1 over x, because I know what that looks like. Right, I know that we talked about that specifically in the previous lecture. It looks like this and this, and it's got a couple asymptotes in there. Right, so I'm thinking maybe I can just transform this one and get to the graph that I'm looking for. Right, so first let's think about this x plus 1. Right, adding 1 to the x has the effect of shifting the graph 1 unit to the left. Okay, so I'm going to clean this up. Right, let's get this out of here. Right, get a clean thing to start with. So I want you to think about taking that graph I had up there and shifting it 1 unit to the left. The horizontal asymptote, I always do that. Let me pick a lighter color so it stands out a little more against the x-axis. Right, the horizontal asymptote is going to stay where it was. The vertical asymptote that was at x equals 0 is now going to get pushed to the left 1 unit, just like everything else, and it's going to be here at x equals -1. And if you think about it, right, we're always kind of double checking in our head if we can. That does make sense because this original, my r of x is undefined, where x plus 1 equals 0, and that is x equals -1. And that is where I just drew my asymptote. So that fits, right? It's making sense. All right, and the rest of the graph is going to have the same shape. It's going to come here, drop off towards my new asymptote, and it's going to pick up here and drop down and look like this. All right, so there's my graph so far. Right, that is, let me label these things. Let's call this g of x, and g of x is 1 over x plus 1. All right, so now to get the only difference between g and my r is this minus here. Right, you remember what putting a minus up on the function does? That has the effect of reversing the sign of every y value. Okay, so if I take this function here, my blue g of x, and switch the sign of every y value, that has the effect of reflecting it across the x-axis. So all the points that were down here on the negative side of the x-axis are going to flip up to the positive side, and all the points that were on the positive side are going to flip over and go down to the negative side. And there's my graph. right? The green line is my final answer. So just so you can kind of see it, let me get the blue line out of here, right? Take out my intermediate steps. There we go. There's my final graph with transformations, right? And again, you notice I did kind of use some of our concepts, right, to double check, right? Like for example, finding the point where the function was undefined. That helped me confirm that, yeah, I did have my vertical asymptote in the right place. All right, so this one looks very similar to the previous one, but that exponent it's a small difference, but it's going to be an important one. Okay, so for this one, let's fall back on our methods. All right, let's start collecting information about this thing. What is the domain of this function? Right. Well, with a rational function, I have to ask the question, where does the denominator equal 0? Those are the points that are not in the domain. So the domain of this function is all real numbers except 0. Okay, so let's see. How about intercepts? Well, to find the y-intercepts, you said x equal to 0, but I can't. 0 isn't in the domain, so this function doesn't have a y-intercept. And to find the x-intercepts, you set the function itself equal to 0. I have to solve this equation, 1 over x squared equals 0, but that doesn't have any solutions. Right? A rational expression equals 0 whenever its numerator is equal to 0, and the numerator on this thing is always 1. Okay, so it doesn't have any. All right, well, that's interesting. Let's see, how about asymptotes? Okay, first, vertical ones. The vertical ones occur where the denominator equals 0. All right, well, that happens at x equals 0, and that's good. That's consistent with my domain, right? So let me put my vertical. As I like to graph as I get things, right? As I get pieces of information, I like to go ahead and just add them right into the graph. So I'm going to put my vertical asymptote there at x equals 0. So let me label these. That was the vertical one. And how about the horizontal one? Remember how we do with the horizontal one? We compare the degree of the numerator to the degree of the denominator. Well, the degree of the numerator is 0, and the degree of the denominator is 2. Okay, the denominator is bigger, which means this function has a horizontal asymptote at y equals 0. So let me add that to my graph. And so far, this is looking awful familiar. Right, this is looking an awful lot like the last one. That should be y equals 0. Okay, so now I kind of know what the answer is. The graph has to start off by the asymptote way off on the left-hand side, and then approach the other asymptote, the vertical one. Or, and here's the thing, there's another possibility. It could start off underneath and drop down. Okay, so this is what I was talking about when I was looking at the last step in our process. I don't know which one it is, right? But I can figure it out easily enough. Let's pick a test value. All right, so let's do some tests. What is, and I need a number that's over there on the left side of my vertical asymptote, so I'm going to check x equals -1. F of -1 is 1 over -1 squared, which is 1. Awesome. So the point -1, 1 is on the graph. And now that clarifies. Now I know it's going to have to start here, tag that point, and then take off up here. Now I want you to think for a minute. Why could it not have started off below? Why could it not have started off below? Let me get another color. It'd be easy to erase. Why couldn't it have done this? Why couldn't it start off below and go like this, for example? Okay, well, the answer to that is our function doesn't have any x-intercepts. In order for it to get to my point over here, should have actually had it touch the point, right? Why couldn't it go like this? Come here, tag my point, then turn around and come back down. Well, it can't do that because to do that, it has to cross the x-axis, and our function doesn't have any x-intercepts, right? So that's not a possibility, and the blue line up there is that side of the graph. Now, how about the other side? Well, look, I'm just going to test again. Let's test x equals 1. That's 1 over 1 squared, which is 1. So it's above the x-axis over here as well. By the same argument, right, it can't cross the x-axis over here either, and that's what my graph is going to look like. Right, there's my final answer. Okay, let's try another one. How about this thing? Okay, this thing is much bigger, right? So let's see. Let's walk through our process here. What is the domain of this function? Well, I need to know where does the denominator, x squared minus 8x plus 15 equals 0. Look, I can factor this. This is x minus 5 times x minus 3. And I get two numbers. The function is undefined at 3 and 5. So the domain is all real numbers except 3 and 5. Okay, so I can't really put that on my graph yet. All right, I don't know for sure that those are going to be asymptotes. All right, and here's why. Right, let's do our simplification. Let's simplify this thing. R of x equals x minus 3, and I already factored the denominator a minute ago. It's x minus 3, x minus 5 times x minus 3. So the x minus 3's cancel. This graph is the same as 1 over x minus 5 with one exception. It's that 3. All right, so let's circle back to that 3 in a minute. I know what this looks like. Transformations. Right? This is the graph of 1 over x shifted 5 units to the right. So my asymptote is my vertical asymptote, 1, 2, 3, 4, 5, is now here. My horizontal asymptote is still at y equals 0. That hasn't changed. And now I know what my graph looks like, right? It's going to start off here and drop it out. These, if you actually find some more points to plot here just to confirm the shape, it actually does drop off really quickly. It stays really pretty close to that asymptote until it gets fairly close to the vertical one, and then it finally drops off really fast. And then on the other side, it's going to look like this. Okay, that's almost it. Right? That's almost it. This graph is saying the function is defined at 3. Right? Because if you go to x equals 3, you go down to the graph, you get this point right here, and it looks like that point is on the graph. It's not. The function is not defined there. So how am I going to show this? Right? I'm going to do, this is very old school, right? How do we show that a point is not on a graph? Well, we put a little open circle there. So I'm going to put an open circle here at 3, and I'm going to fill that in so it really looks filled in. There you go. And that's what my graph looks like. Right? That's how we indicate a point that is not in the domain, but that is still not a vertical asymptote. All right, so let me pause here. Right, let me let you take a swing at this one. See if you can graph this thing going through all those steps. Pause the presentation. Right, take a few minutes, see what you come up with. Then you can start it up again, and we'll go through it together. Right, so I'm going to start where I always start. I'm going to start by figuring out the domain. I need to know where the denominator, x squared plus 4x plus 3, is equal to 0. All right, so this is x plus 3 times x plus 1, and that gives me two numbers. The domain does not include -3, and it does not include -1. So the domain is all real numbers except -3 and -1. Now, hold on to those, right? We know one of two things is going to happen at each of those points. Either there's going to be a vertical asymptote there, or there's going to be a hole there. It's always going to be one or the other. All right, so let's see about simplifying. First thing I'm going to do, I'm going to factor a -2 out of that numerator. That'll just make it easier for me to factor. So it's -2. No, excuse me. Keep it a function. F of x equals -2 times x squared minus 6x minus 9. That is over still x plus 3, x plus 1. Right? That part didn't change. All right, so let's see. Can I factor that numerator? I don't think I can. Right? I don't think I can factor that any further. So I'm not going to get any more simplification than I already have. Okay, and I mean, and that's fine. Right? That's going to happen. There's nothing wrong with that. Okay, so let's see. Next thing I want to think about are the intercepts. Right? To find the y-intercept, I said x equal to 0. Well, f of 0 is all of the terms with the x's in them become 0. All that's left is 18/3, which is 6. So the y-intercepts, the y-intercept, excuse me, only one, is at 0, 6. So I'll go over 0, up 3, 4, 5, 6. There's my x-intercept, my y-intercept. Okay, well, for the x-intercepts, I said f of x, or y, equal to 0. That gives me 0 equals -2x squared plus 12x plus 18 over x squared plus 4x plus 3. Okay, multiply through by the denominator. Right, multiply both sides by x squared plus 4x plus 3. The left-hand side will still be 0. And the right-hand side, the denominator is going to cancel, and all that's left is the numerator. And you see, this is what I told you a second ago, right? A rational expression is only equal to 0 when its denominator is equal to 0. Okay, now what? Well, look, let's simplify it a little. Let's divide both sides by -2, right? Always makes things easier when the numbers get a little smaller. So if I do that, this becomes 0 equals x squared minus 6x minus 9. Yeah, now we're back to where we were a minute ago. This thing doesn't factor. Okay, that does not mean you get to give up. Okay, does not mean you get to give up. It's a quadratic equation. When we have a quadratic equation and it doesn't factor, our fallback is going to be the quadratic formula. Right? If we go to the quadratic formula, we get x equals -b plus or minus the square root of b squared minus 4 times a, that's 1, times c, that's -9. There's the square root, all over 2 times 1 equals. Okay. It's going to get a little messy, but that's okay. This is 6 plus or minus. What's going on under that square root? I've got 36 plus 36, so that's the square root of 72 over 2. And now, look, don't try to simplify that square root, reduce the fraction, whatever. We're graphing, right? Graphing is one of the few times, one of the maybe 2 times, when you're doing math problems when it's okay to go to decimals, right? So that's what I'm going to do. I'm going to go to my calculator, and that tells me that the square root of 72 is approximately 8.46 over 2. So now you have to do this twice, right? 6 plus 8.46 divided by 2 gives you 7.23, and 6 minus 8.46 divided by 2 gives you -1.23. So there are my intercepts, my x-intercepts. Let me get those on my graph. I'm going to go over 1, 2, 3, 4, 5, 6, 7, a little more than 7, and I'm going to go to the left a little more than -1. There are my X-intercepts. Okay, let's see. You have to work. I'm always a little cramped sometimes with the bigger problems. Let's see if we can do the asymptotes up here. Right, we'll do the vertical ones first. Well, the vertical ones occur where the denominator is equal to 0. The denominator of the simplified version, right? But we couldn't simplify anything out. So that's going to be the points where x plus 3 times x plus 1 equals 0. And we already did that. Both of the values we got from finding the domain are going to be vertical asymptotes. All right, so let me put those on here. Right, I've got one at x equals -1. And another one at x equals -3. So -1, -2, -3. That's here. Okay, there's my vertical ones. How about horizontal? Well, for horizontal, we compare degrees, right? The degree of the numerator is 2. The degree of the denominator is 2. So the horizontal asymptote occurs at y equals -2. That's the leading coefficient in the numerator. Divided by 2. That's the leading coefficient in the denominator. That's -1. So I'm going to go to -1 and draw my my horizontal asymptote. Okay, awesome. Now, we've got choices to make, right? Where is the graph? Well, over here on the right-hand side, I know what's happening, right? It's going to have to start up here, drop down through that Y-intercept, cut down here through that X-intercept, and then level off at the asymptote, right? It couldn't have started down below. If I tried to start down below to get up to that X-intercept, that Y-intercept, I would have to have crossed the X-axis at a point where there isn't an X-intercept, right? So I had to start high and go down low. Okay, now, how about the other side? Well, on the other side, I don't have to pick test points over here either, right? I can't start above the asymptote. If I try to start up here and end up going up here, to do that, I have to cross the x-axis somewhere. And I can't because there's no intercept over on that side. So this part has to go like this. Okay, great. There's my middle part. Now, what's going to happen over here? Okay, I need test points. And I know some of you may be sitting there thinking to yourself, well, wait a minute. I know it has to be above the horizontal asymptote because it's not allowed to cross it, and that's not really the case. Okay, the graph can cross a horizontal asymptote here in the middle. Remember when we first talked about horizontal asymptotes? I described what we were doing as thinking about the end behavior of a rational expression or a rational function. Remember how we found the asymptotes? When we were doing it experimentally, I put really big numbers in and I looked at what the graph was doing. Right? The horizontal asymptote tells us about the end behavior of the function. It tells us what's happening as x goes way out on the edges of the x-axis. It tells us nothing about what's going on in between. Right? In between, it is possible for the function to cross over that asymptote. Right? So, so what are we going to do? Well, now we have to go and pick some points. Right? So let me, I was kind of hate to do this, but I got to make some space. So let me clear this out here. and get us some room to write. Got to slow down. It goes better when I try to do this too fast, and I get ahead of what the machine will sense me doing. So there we go. Okay, so let's pick a point, right? Let's try x equals -2. So that's that spot right there, right? F of -2 is, and look, I'm going to put this into the factored version. It's easier to do sometimes with the factored one. So let's do this as -2 times -2 squared minus 6 times -2 minus 9 over -2 plus 3 times -2 plus 1. All right, so the numerator, that's -2, that's 4 plus 12, that's 16, minus 9 is 7. And then the bottom, -2 plus 3 is 1. -2 plus 1 is -1. All right, so this is just -1. And this whole thing is 14. Okay, awesome. My graph paper here only goes up to 10. But that's okay. Right? That's okay. I know that at -2 the graph is way up here somewhere. So I know it's starting up high and coming down. Okay, now, oh boy, here here it gets to be a hot mess. And I'm going to try and dodge actually having to do the arithmetic here, because I got to pick a number between that x-intercept, between -1.23 and -1. So I might pick, for example, f of -1.1. Okay, and let's see. I'm gonna, if you just put -1.1 in there and figure it out, that's great. Bless your heart. I'm gonna try to be a little slicker than this. Okay, when we cross from one factor to another, from one root to another, a polynomial, it's gonna change sign. Okay, so I know that where I got the -2, right? And I know that where this was positive before, it's going to be negative now, right? And then what happens at the bottom? If I put -1.1 in here, -1.1 plus 3 is positive, and -1.1 plus 1 is negative. Okay, so this whole thing here is a negative number, which means I don't know exactly where that point is, but I know it's below the y-axis, right? It's down here somewhere, right? So now I know what my function is going to look like. It's going to come down here, it's going to drop through here, and then it's going to cut through here. And that's my graph. All right, now, there are some exceptions to my polynomial changing sign rule. If it had been x plus 1 squared, okay, then that wouldn't have worked. But hold up, put that idea in the back of your head. Right, put that idea in the back of your head until we talk about solving polynomial inequalities. So we're going to talk a lot more about sign changes in polynomials when you get to a factor, when we talk about polynomial and rational inequalities. For now, if you don't see that little trick, just put the number in. You can have a little work to do with your calculator. That's fine. You're going to get to the right place in the end. Okay. So how about this thing? Right? What are we going to get here? Well, let's walk through our process. The domain. We need to know, where does the denominator equal 0? Well, it doesn't. Right? That denominator is never equal to 0. X squared plus 1 is the sum of two squares. That doesn't factor when we're just talking about real numbers. So the domain is our real numbers. Okay, so what are the intercepts? The y, excuse me, got the label. Let's talk about intercepts. And we'll do the y-intercept first. r of 0 is 0 over 0 squared plus 1, which is 0. Excellent. So the origin is the y-intercept. And that's also obviously going to be the x-intercept, right? Because it's on the x-axis as well. Okay, so to find the x-intercepts, I do this because there might be more, right? Just because I found one doesn't mean I found all of them. So to find the x-intercepts, I'm going to set 0 equal x over x squared plus 1. Multiply, clear the denominator, multiply both sides by x squared plus 1, and I get x equals 0. Good, that was the only one, right? This function has an asymptote, has an intercept at the origin, and that's it. Okay, so let's talk about asymptotes, right? Vertical asymptotes occur where the denominator equals 0. Well, we already saw that it doesn't, right? The vertical asymptotes, you know, there's a tight relationship there with the domain. When we find the domain, we've really already done the work for finding the vertical asymptotes. Okay, so there are none. For the horizontal asymptotes, right, compare the degrees. The degree of the numerator is 1. The degree of the denominator is 2. The denominator is greater, so there is a horizontal asymptote of y equals 0. Let me get that in my graph. That is the x. Whoa, didn't mean that. There we go. That is the x-axis. You notice we're going to have that behavior again with the asymptotes, right? The graph is going to cut across the horizontal asymptote when it gets to the origin. Okay, now I've got my perennial problem, right? Should I, when I'm starting off way over there on the far left-hand side, should I start above the x-axis or below it? Okay, well, I don't know. Let's do some tests. Right? I'm going to put, let's do r of -1. That's -1 over -1 squared plus 1, which is -1/2. Okay, excellent. So we're going to -1 and -1/2. Okay, good. That tells me the left-hand side. Now, let's do the right, because I know what the left-hand side looks like now. It's going to start off here by the asymptote, and it's going to increase to here, turn around, and drop back down to my intercept. Now, at this point, one of two things is going to happen. Whoa, sorry, I put that on the wrong side, didn't I? That was -1/2. It should be down here. So it comes here, drops down, turns around, and comes up. Now, at this point, one of two things is going to happen. Either it's going to turn around and come back down, or it's going to cut through there and then come back down on the other side. And if you think about this, you really know which one it does already. If you think to our conversation about multiplicities, the multiplicity of this 1, of this x in the numerator, the multiplicity of that factor is 1. So we expect the graph to go through the intercept at that point. The same rule is applying here, right? And if you don't believe me, that's fine. Doesn't hurt to check. If you actually calculate r of 1, that is 1 over 1 squared plus 1, which is plus 1/2. Yes, that is what it does. So it's going to cut up, it's going to cut through there, tag that point, turn around, and come back down. And I want to emphasize, let me redraw this. I drew this in a way that was a little dubious. I drew this like those 2 points, -1/2 and 1/2. I drew it like they were the local maximum and minimum values. Like those were the points where the function turned around and started going back the other way. I don't actually know that, right? I don't really know it. So let's draw it like this. Let's not make an assumption there that might have been invalid. That's a better sketch. Okay. All right. So there's our graph, right? Hopefully you're starting to see now. The graphs of these rational functions are really kind of interesting creatures, right? They have much more intricate behaviors than we saw with polynomials. The graphs of polynomials are essentially start at the top or the bottom, up, down, and then take off to the other side, right? These rational functions really can be much more exotic. All right, so let's try another one here. Let's try one more. And again, I'll let you take this one out for a spin. Go ahead and see what you can come up with. Pause the presentation if you need to. Then we'll come back in and do it together. Okay, same process. Find the domain. Where does the denominator, x squared minus 2x minus 1, equals 0? Well, I don't think that thing's going to factor, right? Which is fine. We can go to the formula. This is negative 2, that's the negative b part, plus or minus negative 2 squared minus 4 times a times c over 2 times a. That is 2 plus or minus, what's happening in here? That's 4 plus 4, so that's the square root of 8 over 2. And the square root of 8, that's 2 times the square root of 2. That's 2.82. So this is 2 plus or minus 2.82 over 2, and that gives me two numbers. If I do the plus one, it's 4.82 over 2, which is 2.41. And if I do the minus, it's minus 0.82 over 2, so that's minus 0.41. Okay, now, hopefully you're kind of getting the hang of looking ahead a little bit, thinking about simplifying. Can I simplify this at all? Well, that numerator doesn't factor. That, again, it's the sum of two squares, right? So I can't simplify this at all. And because I couldn't simplify away either of these factors that were giving me these numbers, they are both vertical asymptotes. All right, so let me put those in here. I'm going to go 2.41. That's just about 2.5. So there's my first asymptote. And the second one is really close to negative 1/2. So I'm going to put that more or less right in the middle. Okay. Intercepts. Right? What are the intercepts of this thing? Well, the y-intercepts, r of 0 is, again, all the x terms become 0. Right, so this is 4 over negative 1, which is negative 4. So that's down here. Where am I going? Sorry, over 0, down, I know how to count, down to negative 4. Okay. Now what? Vertical, horizontal, oh, I'm skipping ahead. Intercepts. Y-intercepts. That was the y-intercept. I mean, see, the problem is I'm not labeling things. This is the y. Okay, to find the x-intercepts, remember the x-intercepts occur where the numerator equals 0 and the numerator never does. Right? We can't factor x squared plus 4, so there are no x-intercepts. Okay, how about asymptotes? We already found the two vertical ones, right? We got the vertical ones over here. And for horizontal ones, the degree of the numerator is 2, and the degree of the denominator is also 2. They're the same. So there's a horizontal asymptote at 1 over 1, which is 1. Let me get that on my graph. Right? The horizontal asymptote is here, and that's all I need. Right, now I can sketch the graph. I don't have to worry about testing points. Right, the fact that there are no x-intercepts is going to tell me everything I need to know. On the left-hand side, I can't start high and go low, because to do that, I'd have to cross the x-axis somewhere, and there are no x-intercepts. Right, so on this side, I'm going to start here and come up here. And there's my graph. Same thing over here in the middle. In the middle, I can never cross the x-axis, right? Which means I'm going to have to start low, and before I get to that x-axis, I'm going to have to turn around and come back down. And I get something like this. Similarly, on the right-hand side, I can't start down here and come up, because to make it all the way to that asymptote, I'd have to cross the axis, and my graph doesn't do that. So this section goes here. And that's it. There's my graph. Right? That's what this thing is going to look like. Okay.